Hey guys, welcome back. Today we're going to be talking about energy and work. This will probably be one of the first times that we will be covering a lecture where the the topic is something that is somewhat intangible to most of us. Energy is something that we feel and experience, but not something we can usually put our finger on. That's one of the great things about Newton's laws. We can see an apple fall due to a gravity field, or we can make a lever or something like this, a tool work, all using Newtonian physics. But never before have we ever looked at something, this concept of energy. The introduction of the concept of energy didn't come until fairly late in the physics game, really until the 1700s and 1800s. Did people begin to actually look at this new concept that we now call energy. And it's derived from understanding of something called work. So we're going to talk about these two phenomena. And of course, right here on this original picture here, got two lightning bolts. These are the quintessential manifestations of energy. And believe it or not, if you were to harness these electrical bolts, you could use it to do work. In other words, move things around if we wanted to. All right, so let's do a quick overview of what energy is, because it's something that is a little vague um, in the minds of a lot of people. So let's see what the definitions are as far as physicists are concerned. A combination of energy and matter make up the universe, right? Both energy and matter. Einstein later on would come in and say they're really forms of the same thing. We'll come to that at the end of the lecture series. Energy is a mover of substances. It's both a thing and a process. This is really strange, right? It's both a thing and a process. Observed when it is being transferred or being transformed, right? Here we see this process occurring in these two objects here. Here we see a piece of metal that has been heated up. So in this case, it's been transferred into the metal and now it's glowing. And here it's being transformed from electrical current into light energy. And it's a conserved quantity, which means that it follows the laws of conservation. Just like momentum is conserved, energy is also conserved. All right, so what is energy? Well, energy is simply a property of a system that enables it to do work. And anything that can be turned into heat. Okay, that's what energy is. So an example would be electromagnetic waves from the sun would be a form of energy. And those electromagnetic waves that hit us in our eyes is referred to as visible light. Matter. So matter is usually understood in contrast with energy. So matter is a substance we can feel, we can see, smell, and feel, and it occupies space. Energy is something that we don't always see. It's something that we don't always smell, and it's something we don't always feel, but we can calculate its existence. And as we go forward in the class, you'll find that energy and matter are very closely linked one to another. All right, so how do we come up with this concept of energy? Well, to understand energy, you have to understand work. So work is just a relationship from Newton's second law. And so work just involves force and distance. So it's really just force times distance. And in equation form, it's work equals force. Remember, force is a vector times distance. And it's a scalar quantity, right? The amount of work that you do is not the same thing as the direction that the work is occurring in. That might be a little strange considering our work on vectors, but nonetheless, it's true. So the amount of work that is done is true no matter which direction you do it in. So up here we have a pitcher up on a pitcher's mound, and notice that as he's coiling the ball back and he's moving forward and throwing it, that whole time he's holding the ball up until this last frame. He's doing work on the ball. He's putting force, right? Obviously he's putting a force on the ball, and the distance is the period of time that he's holding the ball as it arcs out of his hand. Okay, so two things can occur whenever work is done. Application of a force and movement of something by that force, right? That's all implied by this equation right here. All right, so let's look at how this equation tends to play out, right? So there's two examples. So here we see a two-story building under construction, and they are lifting up loads or masses to the different levels. And we can ask ourselves, which is more work? Is it, See, let's see here. Twice as much work is done in lifting two loads one story high versus lifting one load the same vertical distance, right? The reason is pretty straightforward. Force needed to lift twice the load is twice as much, right? Force times distance, twice as much force. There it is. Twice as much work is done in lifting a load 2 stories instead of 1 story. The reason? The distance is twice as great, right? What are the units of work? Well, if we just put the equation together, work equals force times distance, and then we go ahead and we plug in what the units for force are, which is the Newton, we realize it's really just newtons times meters. And this unit called a Newton meter is what we call a joule, which gets this mark of a J. So it's the amount of work that is done. So you'll see these results usually reported as Newton meters or joules. All right, so in contrast with work, there's something called power. And power it's very similar to work except with one small difference. And that is that it's a measure of how fast work is done. So in equation form, power is equal to work divided by time. Another way of writing that is force times distance divided by time is going to equal power. So if you're doing something very slowly, even though it gets done, it's not with much power. But if you do something very rapidly, even if it's over a very short distance, you could be exerting quite a bit of power to make that happen. So here's some examples, right? The first one, a worker uses more power running up the stairs than climbing the stairs slowly. Makes sense, right? Because power is work divided by time. So if you take more time, you're going to exert less power, right? And then there's a series of power arguments in here. If you'd like, you can pause the video and you can read through them. But they make sense, right? If you do something faster, you're going to have more power, even if it's the same amount of work. And so the unit of power is something that we're very familiar with. It's the joule per second, named in honor of James Watt, who developed the steam engine, and it's something called a watt, right? So 1 joule per second is equal to 1 watt. And here's the derivation, right? Power equals work divided by time, which means that power is joules per second, and joules per second equals a watt. So 1 kilowatt equals 1,000 watts. This is usually how we pay attention to our electric bills, right? It's usually given in kilowatt hours or kilowatts. And be careful not to confuse watts, which is marked with a W, right? It's a unit W, with work, which is also symbol W, right? Here's W, but up here the W is work, and down here the W is watt. Make sure that you understand the difference between these two as we go forward in the class. All right, so now that we've gone over what power is, and we kind of have at least a general understanding of what energy might be, we can start actually looking at what energy is and what it does, and how it plays a role in the systems that we've been describing really all along since Newton's first law. We just haven't dealt with the specifics of the energy aspect. So it turns out that there are two kinds of what we call mechanical energy. And so mechanical energy is due to position or to motion or both. Right? Just kind of put that in your back pocket if that doesn't make sense to you. By the end of the lecture, hopefully it will. So there are two forms of mechanical energy. There's potential energy, which is stored energy held in readiness with the potential for doing work. So a form of potential energy would be, say, like a Duracell battery or a copper top battery. This is stored energy. It's stored chemical energy that can do work by creating an electrical current that then can turn a motor or run a light bulb or whatever it is that it's going to do. But it's got the potential to do it. Another example would be a stretched bow has stored energy that can do work on an arrow. So when you pull that bow string way back with the intention of shooting an arrow off, when it's pulled all the way back, it's got stored energy in it. It can do work. If I let go of it, it'll actually put the bow into motion. But before I stretch it, it has no potential energy. It can't do anything. I have to put energy into the system to make that happen. All right, so the other type is kinetic energy. And kinetic energy is the energy of motion, and it depends on the mass of the object and square of its speed. So this actually has an equation. We're going to come to the potential energy equations as we go through the class. But the kinetic energy equation for a moving object is this thing right here. So it's kinetic energy equals 1/2 times the mass times the velocity squared. All right. And the result is that if the object speed is doubled, then the kinetic energy is quadrupled, right? So by doubling the speed, you quadruple the energy. We'll do a couple of calculations shortly that demonstrate this point. So let's look specifically at potential energy. And one of the best forms of potential energy to look at is gravitational potential energy. So it's basically the potential energy due to elevated position. So in this case, we see a dam, and behind the dam is water. And this water is all piled up behind the dam. And basically, if the dam was to break, the water would run down this canyon in this direction. This is actually Hoover Dam, one of the most important dams in all of mainland United States. And it also produces a ton of electricity. And it takes advantage of the fact that this huge amount of water is all piled up behind it, and it has potential energy. It's like a giant battery that just converts this potential energy into electricity as it runs through the dam. So what are some examples of potential energy other than the water in the elevated reservoir? A raised ram on a pile driver. A pile driver is used to push large stakes into the ground like a giant hammer. Another form of potential energy would be just taking a rock and lifting it up above the ground, right? It has the ability to do work. And you're giving it a greater ability to do work as you put more potential energy into the system. So it's equal to work done. So the amount of work that you put in, remember work is in joules, and that's force required to move it up times the vertical distance moved against gravity in lifting it. So the amount of work is equal to the amount of potential energy. That's really neat because that means we have a relationship for once, right? With kinetic energy, we already have that relationship. So in equation form, gravitational potential energy, or which is PE, is equal to force times the height, right? The height or the distance, same thing. So H equals height, replace F with mg, and you get this nice gravitational potential energy equation. Mass times gravity times height. So now let's talk about kinetic energy and work of a moving object. So it's equal to the work required to bring it from rest to that speed, or the work the object can do while being brought to rest. In other words, the amount of kinetic energy is the amount of work done to bring it up to speed, to slow it down, right? So the change. In equation form, net force times distance equals kinetic energy. Or, look at this, kinetic energy equals force times distance, which is work again. But this, in turn, equals 1/2 mass times velocity squared. Now, you might be saying, how in the world, where's this 1/2 and the squared coming from or whatever? The derivation requires some calculus, so don't worry about us covering it, right? It's beyond our math level. So at this point, you're just going to have to understand that this is just kind of coming from the math gods to you as this work energy theorem that we have. Force times distance equals 1/2 mv squared. For kinetic energy, only for kinetic energy. Potential energy is a little different scenario. So in that work energy theorem, we can talk about why we know how the doubling of speed quadruples the work, and so on and so forth, or actually quadruples the energy as well. So the work energy theorem says a gain or reduction of energy is the result of work. So if you want to put work into lifting the rock higher, you're going to get more potential energy out of it, right? In equation form, work equals the change in kinetic energy. Pretty intuitive, actually, if you think about it. So let's go ahead and run these equations. So if velocity equals 2 meters per second, let's kick it into the kinetic energy formula. And you can see we do the calculation. If it's going 2 meters per second, then we have a kinetic energy of 2 joules, right? Of course, we're assuming that mass is equal to 1 kilogram. Over here, if the mass is equal to 1 kilogram again, velocity is doubled. The result is 8 joules, which is a quadrupling over the 2 joules when we run through this. So a small increase in velocity has a huge effect in terms of multiplying the amount of energy or work done in a system. So it doesn't just apply to things increasing in speed, it also applies to decreasing speed. Remember that one of the first forces we dealt with in the series of lectures is friction, right? So reducing the speed of an object or bringing it to a halt using friction. Friction is a force. So applying the brakes to slow a moving car, work is done on it, right? The friction force supplied by the brakes times the distance over which that occurs. Okay, so it works both ways, not only when you speed up, but when you slow down as well. Which leads us to a really important concept of energy, which is the law of conservation of energy. And essentially what it says is that energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy never changes. Okay, it gets a little murky when you get Einstein involved in this, but this is pretty much a true axiom almost everywhere else, right? So for example, a windmill, as the wind goes by, it's got mechanical energy, it's got some velocity, and as it goes past the windmill, it spins the blades, and the blades actually turn it into electrical energy. The result is that the wind on the other side of the windmill actually slows down, right? So it's transferring that energy into electrical energy. So the same thing here in the solar cells, right? It takes light and heat energy and converts it into electrical energy. The dam down below here is simply taking the mechanical energy of the water coming through the spillway, and before it goes through the spillway, actually, it could potentially turn an electrical turbine, or the fact that it's just going from high to low is actually indicative of a transfer of energy. So in conservation of energy, we can kind of ponder the following situation. So consider the system of a bow and arrow. In drawing the bow, we do work on the system. In drawing, in pulling back the bow, in drawing the bow, we do work on the system and give it potential energy. When the bowstring is released, most of the potential energy is transferred to the arrow as kinetic energy and some as heat to the bow. Right? So this is what you're doing, is you're just doing a transfer. As she pulls it back, there's potential energy here in the system. There's an arrow, it's very thin, it's hard to see in the picture. This is a scope used for aiming. And basically when she lets go, when the archer lets go and the bow starts to move, the string will return to its original shape. We all kind of know this since we were kids. But what's really profound is that the potential energy in the bow is transferred into the kinetic energy of the arrow. So the further back she actually pulls on that bow, the more potential energy, and therefore the greater the kinetic energy. And there's heat loss also. There's some of the heat is lost to the bow. Cool, so as we're going through this, you might notice something pretty rapidly. That, remember, momentum was mass times velocity, and kinetic energy is 1/2 mass velocity squared. So there's some similarities between the two, right? Both are properties of moving things. But there are some important distances, and you want to make sure that you do not confuse momentum and kinetic energy for one another. This is a common error. First off, momentum is a vector quantity, and therefore is directional and can be canceled, right? You can have momentum going one direction, another momentum going that way, and the net momentum could be canceled to zero, right? But kinetic energy is a scalar quantity and can never be canceled, right? It is what it is. When you have a ball going some velocity in that direction, the energy is whatever it is. When you have a ball going the opposite direction, it doesn't cancel. It's just simply two balls with energy and becomes twice the amount of energy. Velocity dependence. Momentum depends on velocity, whereas kinetic energy depends on the square of velocity. So kinetic energy actually gets very large very fast. So an object moving twice the velocity of another with the same mass has twice the momentum, but 4 times the kinetic energy, right? So energy increases with the square, whereas momentum is a linear, or what we would call a linear 1-to-1 increase. So now that we have an understanding of what conservation of energy is, that we can transfer things from kinetic energy to potential energy back and forth, and we don't actually lose the energy, we can use that to our advantage. And that is that we can go ahead and design things called machines. We've been doing this since the Stone Age, right? Tools and machines to be able to help us transfer energy from one place to another, or type to another type. So a machine is a device for multiplying forces or changing the direction of forces. It cannot create energy, but can transform energy from one form to another or transfer energy from one location to another. It cannot multiply work or energy. Why? Because these things are conserved quantities, right? You can't create nor destroy energy. You can simply transfer it. So the principle of a machine is simply this, right? The conservation of energy concept, that work in is equal to work out. So in this situation, the input force times the input distance is going to equal the output force times the output distance. So we can manipulate force and distance on this end, and it will change the force and distance on the other side, right? We increase the force here, it's going to increase the force here. But if we know what the force is here and we change the distance on this side, we can actually manipulate the force and distance over here. Let's see how that works. So the simplest machine, for example, is a lever. And it rotates on a point of support called the fulcrum. So here's the fulcrum right here. And it allows small force over a large distance and large force over a short distance. So in this case, imagine I've got this huge lever and I have the fulcrum at this position here. So there's a whole lever on this side and a much smaller lever on this side. So the distance times force, or the amount of work actually I should say, done over here, distance times force. If I have a large D, I swing it through a larger distance, I don't need as much force. But the result is that I get a large force over on this side in a very small distance. And we've all used a big long stick at some point in our past to try to dig out like a big rock. You know, shovels do this, for example. You stick the shovel in the ground and you pull back on it. And basically you're using distance and a smaller amount of force to be able to put a lot of force at the tip of the shovel, but over a very small distance. So pulleys are machines that operate like a lever with equal arms, actually, as opposed to having one small and one large one. And it changes the direction of the input force. So, for example, this pulley arrangement can allow a load to be lifted with half the input force. So here we see the direction of the force is being changed, right? So you can see that the output is up, but the input is down. So here we want to lift this block up. So what is helping this person lift the block up? Well, the fact that they're pulling it up around here, there is definitely a resistance force, an output force here that is holding the situation up. So not only is the roof or the ceiling of the pulley that the pulley is attached to pulling up on the pulley system, but this person is also exerting some of that force. It turns out half the force on their behalf, half of it is being done by the pulley, and it makes the block much easier to pick up. So another important thing to think about when we deal with engines or machines or anything like this is efficiency. So it doesn't do much good to start transferring energy and work through a system of machines and levers and whatever. If it turns out the amount of work that you're putting into it is not giving you a good enough return. So we have to look at this thing called efficiency. And the efficiency is just the percentage of work put into a machine that is converted into useful work output. So in equation form, it's just simply the amount of energy we got out of it that was useful divided by the total amount of energy we put in. So there's a lot of kind of vague concepts in energy. And energy is one of those things that you just kind of got to get a feel for. You know, it's something that does not necessarily come right to you. You know, if you drop a rock, how much energy is being released as you drop that rock? The equations actually tell us. But the idea that there's even energy associated with that seems kind of bizarre to a lot of people. And it was bizarre to physicists for a long time until somebody actually figured out the details of what happens with energy and matter. Mainly that was a man by the name of Einstein. I'm sure you've heard of him. All right, so let's do some practice problems to kind of get a better handle on what is going on with work and energy. So here's a question. How many joules of potential energy are transferred to a 100 kilogram steel beam hoisted to the top of a 300-meter tall skyscraper? That is a very tall skyscraper. That would be basically as tall as the World Trade Center, or maybe even slightly taller in some respect. That's a very tall skyscraper. All right, so 100 kilogram steel beam hoisted 300 meters. Let's do that calculation. Okay, so we have this building, very tall skyscraper. Okay. Oh, this is pretty neat. This is a brand new program for me, so it's going to be tracking my little sketches over here if I want to make edits, I guess. We'll go ahead and put a tower on here just for fun. And we've determined that this tower is 300 meters high. And so we've hoisted through a, I don't know, say a crane. So there's a crane at the top of that building, and it's lifting up a steel beam. It's lifting it up there. And it wants to know what the potential energy is equal to. Well, this is a pretty straightforward calculation, because if we can remember that potential energy equals mgh, it falls right out for us, right? This beam was, by the way, 100 kilograms. Potential energy equals 100 kilograms times 10 meters per second squared times the height, which is 300 meters, and we get this really cool solution, right? We get 1,000 kilogram meters per second squared times 300 meters, and let's move our number over here so we don't lose our cursor. Potential energy, let's keep in mind that this value right here, kilogram meters per second squared, equal newtons. So 1,000 newtons times 300 meters. Potential energy is a very large number, 300,000 Newton meters, also known as a joule. Okay, so that's our answer. That's a lot of potential energy. Cool, so we were able to figure out the amount of potential energy that was transferred into that beam. All right, now if that thing was to ever fall on the ground, God forbid, the amount of damage that would be done, because the energy would be huge. All right, so let's do another one. So how much power is required to lift a 30 kilogram barbell a total of 0.8 meters in 2 seconds? This would basically be like a little weight lift, right? Not a lot, or like a bench press, but a small amount of bench press. So how much power would be required to do this lift? All right, let's do that. So in this case, we got force and distance and time, exactly what we need. So let's open up our program again. All right, so we have a, I don't know, we have a bench. Usually these benches have a bar, and then on it is a circular bar that is lifted by a weightlifter. Okay, so the weightlifter is going to be lifting this thing up and down, and we want to know how much power is required to do it once. And so this total distance is 0.8 meters, and they're going to do it in 2 seconds. Okay, and the total mass of the barbell is actually not very heavy. So in this case, M is equal to 30 kilograms. Cool. All right, so let's see how much power is required. Remember, power equals work divided by time. And work is just force times distance over time. So we know what force times distance is here. Okay, so force is mg d, right? Because we know that d is right here, but force is mg. We know that time is actually going to be 2 seconds, but let's leave it as t for now to simply put that in the calculation a little later. Okay, let's take all this, fill it in here. Power is going to equal the mass, which is 30 kilograms, times gravity, which is 10 meters per second squared, times the distance, which is 0.8 meters, divided by time, which is 2 seconds. All right, so let's stick it in our calculator, and what we're basically doing is 300 times 0.8. Actually, you might be able to do this in your head, right? What's 30 times 10? It's 300 times 0.8. So it's not equal to 1 quite. Yeah, if you're able to figure it out in your head, you'll realize that it's equal to 240 kilogram meters per second squared, also known as a Newton meter, or a joule, divided by 2 seconds. So that means the amount of power is simply 240 divided by 2, 120 watts. Cool. Let's do some more. All right, so the next question is, what is the kinetic energy of a 500 kilogram object, it should say object, moving at 100 kilometers per hour, which is to say 27.8 meters per second. So I've done that already for you, so you know what that is. So we know 500 kilograms, we know the speed, plug and chug, right? This is just going to be a simple kinetic energy question. Okay, so the velocity of our object is equal to 27.8 meters per second. All right, and our mass is 500 kilograms. And we want to know what the kinetic energy of this thing is. Okay, let's see here. Well, the kinetic energy equation is equal to 1/2 mass times the velocity squared. So kinetic energy is going to be equal to 1/2, let's just fill it in. Mass is going to be 500 kilograms. Velocity is 27.8 meters per second squared. This is really important. Don't forget about that squared. That's huge. All right. Let's keep going here. Kinetic energy is going to equal, we can get rid of that 1/2 simply by multiplying it into the 500. So it's going to be 250 kilograms. And we need to figure out what that is, right? So let's switch over to a calculator. Actually, I'm going to pull out my cell phone, and I'll be right back. Okay, so I put it into my cell phone, which just happens to have a scientific calculator in it. And so this 27.8 squared is equal to 773 meters squared second squared, right? You also have to square the units, meters squared and seconds squared, right? So you get this really strange value. But it actually isn't so strange because it gives you something in Newton meters, which is also known as a joule. So the kinetic energy then is just equal to those two put together, and I'm sticking it into my calculator. 250 equals 193,210. And of course, we wouldn't necessarily take it up to the 210 because significant figures say that we need to say just these first three. So we're at 193,000 joules, right? So this object, even though it's going only 100 kilometers per hour, which is 60 miles per hour, by the way, 27.8 meters per second, that's pretty fast. I mean, it's fast enough. But its mass is relatively large, but it's still nowhere is near the potential energy that's in that bar that we lifted at the top of the building in the very first question we did, right? So that bar, that 100 kilogram bar, 300 meters up in the air, still has 50%, over 50% more energy in it than this 500 kilogram object. So 500 kilograms is like a car. That's a large amount of mass going at a very high speed. So the amount of energy here is actually less than that 100 kilogram bar has been lifted to the top of the building. All right, let's do one more. All right, so Nellie Newton applies a force of 50 newtons, right? So Nellie Newton, I told you in an earlier lecture we'd be seeing her again. 50 newtons to a lever which is moved a certain distance. We don't know what that distance is. We're just going to say it's d. If the other end of the lever moves 1/3 as far, okay, show that the force it exerts is 150 newtons. Okay, let's do that. All right, so we're told that Nellie Newton is going to exert some force on a lever. Right, so there's some lever, it's a fulcrum. This is a fulcrum. So there's some lever, and as Nellie Newton pushes down in this direction, the lever is going to pivot around this fulcrum and move up over here. And so we know that she applies a force of 50 newtons on this side, some distance. It doesn't tell us what the distance is, it just simply says it's some distance. And so that distance we're just going to call d. And on the other side, we know that it moves 1/3 as much as it did on the other side of this lever. And so 1/3 d times some force, right? And it wants us to show that this force here is going to equal 150 newtons. The resultant force is going to equal this. All right, let's see if we can make that happen. Well, first off, 50 newtons times d equals d thirds. All right, divide both sides by d thirds. And when you do this, you can actually see the calculation in your head how it's going to play out, but you'll recognize rapidly that you can just multiply the top and the bottom by the reciprocal, or you just recognize this cross cancels, that becomes a 1, and 50 newtons divided by 1/3 is the same thing as multiplying it by 3. Why can you do that? Because, well, let's go ahead and do this. Let's just show that you can multiply the top and bottom by 3. What does that do? 3 over 3, that's a 1. That's a 1, that eliminates the denominator, but you still have a 3 up here, and that turns it into 150 newtons, because this all cancels out. So we showed how Nellie Newton was able to get 150 newtons out. We didn't actually even know the true distance. We just knew the ratio of the distance. So that's kind of a powerful tool in physics. And sometimes you don't always know the answer, but you can still get the proper result. Cool. So we've had a couple of really neat little equations to play with here. So let's have a look at what we came away with, right? We discovered that work equals force times distance. That power was just work divided by time, so this gives us a unit called watts. And here we see again the units for work, which is also the same as the units for energy. Force times distance is going to wind up being in this unit called the Newton meter, or better said, the joule. Gravitational potential energy is force times the height, which is to say mgh, right? Potential energy equals mgh. This is a really useful relationship to have. And then finally, kinetic energy is 1/2 the mass times velocity squared. So you've got a really good homework set that's going to deal with energy questions. I think you're really going to like some of the experiments that they show you in there, and how energy and power and work are all very closely related to one another. If you have any questions, as usual, feel free to message me either through the discussion board or through the email system. Until next time, bye.